So we went over an example of trigonometric substitution last time before finishing the lecture. And well, I mentioned that I'm going to go through a different way than the textbook does. So rather than memorizing a bunch of information on a table on your textbook, this triangle that we built from the either hypotenuse and side or side, trust me, it's going to save us like 6 steps. And actually, I'm going to do one example at the end of the lecture, the way the textbook does, so you can compare, so you can see what I'm really talking about. So, okay, let's have a look at another integral. So, well, number one, it would be great to focus on, hold on, why you say that, this one. So let's only focus on the quantity inside of the radical. In other words, we're going to find out what quantity squared equals to 4 minus what quantity squared equals to x squared. Alright, so what are those quantities? 2 and x, alright? Now, another thing, what's this? A difference of squares or a sum of squares? It's a difference of squares. That means the first term should represent the hypotenuse of the triangle and the second term should represent one of the sides. Which one is it? Doesn't matter, but I always suggest to use the one that is opposite to the angle, to the acute angle that we draw on the triangle. So let's draw that triangle. This is our theta, our reference angle. And well, so this 2 right here again, this is hypotenuse, this is side, so 2, and the side it's going to be x in this case. It doesn't matter which one is it. Again, I just suggest that you take the opposite to be the x. Alright, well, the missing side right here, we can use the Pythagorean theorem. You don't need to spend the whole time setting up the Pythagorean theorem, because ultimately you will get back to this radical, 4 minus x squared. Okay, so we have the 3 elements that we need for trigonometric substitution. Alright, number 1, the idea is to write this radical, this ugly looking radical for which the u substitution didn't work, and we need to write it in terms of a trigonometric function. So we're going to use our SOHCAHTOA ratios to represent that radical. And number 1, well, actually we have 2 options to write that quotient. Number 1, the radical over 2 or the radical over x. Which of the 2 looks simpler from the 2? Radical over 2. Alright? So radical over 2, that's square root of 4 minus x squared, divided by 2. And which trigonometric function is this? Cosine. Okay, cosine. Okay, let's solve for the radical. That's 2 cosine theta. And that's going to be our first ingredient in the substitution. We need 2 pieces of information in addition. Alright, we need something to replace the dx. And again, let's recall that dx comes from differentiating an x. Well, so how do we relate this from the triangle? Well, we have an x here, and we have 2 options. Number 1, x over radical, which is really ugly, or x over 2, which is a lot simpler. Let's go with the simpler one. X over 2. And that equals to, I believe it's sine. And x equals to 2 sine theta. This is number 2 in our substitution. And well, from here we will take the derivative. We will differentiate both sides. That's going to be dx equals to 2 cosine theta d theta. That's number 3 in our trig substitution. So we have everything that we need to go back to the integral in the world of x, send it to the world of theta, solve the problem in the world of theta. Once we do that, let's go back to the world of x by relying in our substitution from the triangle. You'll see. So number one, the integral, okay, dx will be replaced with the quantity 2 cosine theta d theta divided by, okay, notice we have this quantity x squared, but we have an expression for x, don't we, which is 2 sine theta. And well, we will no longer write down this radical. That's actually the purpose of trigonometric substitution. Get rid of those radicals and write it in terms of trigonometric substitution. And for the radical, we got 2 cosine theta. Inside of the parentheses, that's a 2 sine theta. And that's the integral. And well, most of the times these trigonometric integrals may look ugly at first glance, but once we have a look at them, you'll see how this will simplify very nicely. Check this out. So we can cancel 2 cosine with another 2 cosine, and then from here, if we keep, so in this case we need to square the 2 square the sine to get the theta equals 2 squared, which is 4 sine theta, sine squared theta. Alright, on the one hand, let's take that 4 in the denominator outside of the integral as a 1/4 integral of d theta over sine squared theta. Okay, we cannot integrate this sine squared theta. Yes?
What happened to the dx at the end? The dx's, why is there only one here and then over here?
Oh, yes. This is a typo. There's a double dx. So let's just erase it. Thank you. So, well, we cannot integrate sine squared in the denominator, so let's use identity. So what's the equivalent of? Well, 1 minus cosine squared in the denominator, so that'll give us 2 terms in the denominator. That's going to be like very tough to compute. Any cosecant squared in the numerator, right? Cosecant squared theta d theta. And well, this is one of those direct integral formulas, the integral of cosecant, which is cosecant squared, which is similar to the integral of secant squared, but the integral of secant squared is tangent. The integral of cosecant squared is negative cotangent, right? And we're done with the calculus. Let's just go back to our triangle here. Well, cotangent, SOHCAHTOA. What's SOHCAHTOA for cotangent? Cosine over sine. But well, how about, SOHCAHTOA in terms of hypotenuse? Yes.
You rely about the side opposite to angle over the side.
So cotangent is. So in other words, well, number one, it's cotangent is adjacent over opposite. Adjacent, which is the radical, over opposite, which is x, plus c. Well, how about we just get rid of this parentheses? So that's the square root of 4 minus x squared divided by 4x, but don't forget the negative, and plus c. And we're done with this one. Let's do another example. Okay. For the next example, what do we have? We have the integral of the x over the square root of 9x squared plus 4. Well, we're going to see something different here. Number one, let's write this as a quantity squared plus quantity squared. So what quantity squared would equal 9x squared? Isn't it 3x? And what quantity squared would be equal to 4? 2. Now the question is, do we have a sum of squares or do we have a difference of squares? So in this case, the sum of squares, both terms of the sum of squares would represent this time the two lengths of the triangle, not the hypotenuse. Let's recall that. Let me go back to the first page. So coming back to the Pythagorean theorem, that's hypotenuse squared equals side squared plus side squared. In some cases, we're given the lengths of the two sides. The question is, what's the length of the hypotenuse? In other cases, we may be given the length of the hypotenuse and the length of one of the sides. And the question would be, what's the length of the other side? Well, so in this case, when we're given the two sides, that's going to look like a sum of squares. When we're given hypotenuse and one of the sides, that's going to be a difference of squares. And again, the first term always represents the hypotenuse because that has to be the longest side of the triangle, and it should make sense to subtract a smaller quantity to a larger quantity, because if we do it the other way around, we get a negative quantity inside of the radical and we are in trouble with imaginary numbers, which is not what we're going to deal in this class with. So alright, so that means side and side. So theta, and in this case it doesn't matter which side is which. However, the side containing the variable, my advice is that you label that for the opposite side. That's a 3x over 2. And well, if you did Pythagorean theorem using these two pieces of information, you should get back to the original radical. That's the square root of 9x squared plus 4. Well, so we got everything. We need to start performing the substitution. Well, we need an expression for the radical. We don't want this radical. We want to turn that into trigonometric functions, because again, otherwise, if we try and if we attempt a u substitution, well, u equals 9x squared plus 4. Take the derivative of that. There's nothing wrong with getting 18x. However, we can put the 18, but we don't have that factor of x that we would stand the du part of the problem. So that's why we are doing this new method. Use this trigonometric substitution. All right. So to get an expression for the radical, so we have a couple of options. So number one, the radical over the constant, which I think it's the simplest option, and the radical over the x, over the variable. That's gonna complicate it. Let's go with the easiest of them. So that is the square root of 9x squared plus 4 over 2. And what trigonometric function is that? Almost. Secant, which is the reciprocal of cosine. Yes, these two, the two sides that we're relating is hypotenuse and adjacent. However, depending on the order, and in this case this is secant theta. Solve for the radical. Square root of 9x squared plus 4 equals to 2 secant theta. Okay? And well, so that's number one in the substitution. Number two, we need to find the substitution for the dx part. So this is what we do. Again, the dx comes from differentiating the x. So which sides of the triangle contain that x? It doesn't matter if it has a coefficient. Isn't it the 3x? Okay, we will deal with that 3 in a second. So we're going to do, number one, we have a couple of options. 3x over the radical, which is too ugly, or 3x over 2. Much better, 3x over 2. All right. 3x over 2 equals to tangent this time. And well, let's solve for x. X equals to 2/3 tangent theta. That's number 2, which we're not going to use anyway, but we still need it to get the dx. So dx equals to 2/3 secant squared the theta. All right, we got everything we need. We got everything we need. Let's go back to our integral. Well, So let's see. Dx, well, actually, let me write it this way. So that's the integral of the radical. What's the radical equal to? 2 secant. Let me change this to 1 and dx. It's easier to see. So 2 secant theta. That's 1. And what's dx? This whole thing. 2/3 secant squared theta d theta. And well, number 1, check this out. Cancel out one of the powers of secant, and that was supposed to be a 2/3. 2/3, cancel the 2's, and let's take the 1/3 outside of the integral, and secant squared divided by secant, isn't it just a secant? And what's the integral of secant? That's the derivative of it. ln secant theta tangent theta plus tangent theta plus c, and we're done solving the problem in the world of theta. Let's go back to the world of x. Well, secant, what's SOHCAHTOA for secant in accordance with the triangle? So secant, which is hypotenuse over adjacent, well, isn't it the radical over 2? And what's tangent? That's opposite over adjacent, 3x over 2 plus c. We're done. Let's do one more, and then I'm going to go back to this example to letter C, but actually doing it the long way, what the textbook suggests to do. Yes?
Yeah, one question. What was the reason why you said both vectors were sides?
Oh yes, coming back to the Pythagorean theorem. So this is hypotenuse squared equals side squared plus side squared. So when we're given a and b in a Pythagorean theorem problem, well, that means we're given the lengths of the side, and the question is what's the length of the hypotenuse. But otherwise, it could be the case that we're given the length of the hypotenuse and one of the sides. So the question is what's the missing side. And well, when we have the sum of squares, this should represent, each of them should represent the length of the side. But when we have a difference of square, the first term should represent the longest term or the longest side of the triangle, which is always the hypotenuse. Right? Let's do one more. The next example, the next and last example, it's actually a definite integral, which by the way also doesn't look like a radical. It has a 3/2 power. Well, sure, we can make this look like a radical because, well, whenever we have rational exponents, the denominator of the rational exponent indicates the index of the radical, which in this case it's 2. That's going to be the square root, x squared plus 1 cubed dx. Okay, now let's write this integral. I know this is going to be very simple to do because there's really no crazy coefficients, but just so I can follow the same steps as in the other examples. Now the question is, what quantity squared equals x squared?
X.
What quantity squared equals 1? Alright, what do we have? Sum of squares or difference of squares? What do these two terms represent? Does one of them represent hypotenuse? No, these are the lengths of the sides, right? So side and side. Okay. Theta equals, well, we have two options for the side, but again, my advice is to have the opposite side to be the one that contains the variable x or y, your favorite letter, or the given letter, that whatever it is. So how about x over 1? I mean, not x over 1, x and 1, and this will be x squared plus 1. Now, again, let's find ratios. We want to rewrite this ugly looking radical, send it to the world of trigonometric functions by having a quotient here in accordance with the triangle. So we have a couple of options. Number 1, radical over 1 or radical over x. Which of the two is the simplest of them? Radical over 1. And what trigonometric function is that? Secant. Okay, secant. Okay, so, well, let's divide this by 1. That's just the radical. The square root of x squared plus 1 equals secant. Score. That's number 1. Number 2. Okay, we need to find a substitution for the dx. Recall that dx comes from differentiating the x. That means we should use x as one of the next quotients, and we have a couple of options. X over this ugly looking radical, which is not the simplest option, and x over 1. How about x over 1? Keep it simple. What trigonometric function is that? Tangent. Alright, tangent theta, x over 1, which is x, and dx equals secant squared theta d theta. We got everything we need to send this integral from the world of x to the world of theta. Solve the problem in an easy way in the world of theta and then go back to the world of x. So this will be equal to the integral, and I'm going to skip the limits for now. I'm going to write those at the very end. And well, the radical, we said this should be secant. Something I forgot over here is this cubed right here. So secant theta to the third power, and dx, which becomes secant squared theta d theta. So that's equal to, okay, secant cubed and secant. Cancel these two with 2. That's 1 over secant. And well, can we integrate secant in the denominator? We can use trigonometric identities. What's 1 over secant? Oh, this is easy to evaluate, isn't it? Integral of cosine is sine theta d theta. Oh, plus. Okay, not plus c, not yet, because this is a definite integral. Okay, so number 1, before we can evaluate the limits of integration, we need to go back to the world of x. Okay, let me move this over here. Let me move this over here. Whoops, what happened here? It got bigger. All right. So this means SOHCAHTOA with a triangle, that means sine. So sine, which is opposite over hypotenuse, that's x over the radical. Do we agree with this? Okay, so x over the square root of x squared plus 1, and in this case we put the bar to indicate that we evaluate the integral from 0 to 1. Alright, so upper limit minus lower limit, that is 1 over the square root of 1 squared plus 1 minus, do we really need to plug in that 0? Because that's a 0 divided by 0 squared, which is 0 plus 1, that's the square root of 1, no need. Big 0. We're good with this. 1 squared, which is 1, plus 1 is 2, that's 1 over the square root of 2. And that's the final answer, but you might want to rationalize this denominator. WebAssign might ask you to do this. So that's the square root of 2 over 2. Sounds good? Alright guys, so this is what I have planned for this section. However, let me see if I can add another page. Great. Alright. So I'm gonna go back to example letter C and do it the way the book does it. So, I mean, if you prefer to do it the way the book does it, memorizing 3 different cases, 3 different substitutions, a bunch of information, that's fine. Let me write that information first. So, what the book tells you to do is essentially, whenever you have the form a squared minus u squared, a squared plus u squared, and u squared, or let me do it the other way, and u squared minus a squared. Those are the 3 different cases. Now, whenever the book says, oh, do you see this form? Well, then just do this substitution here. That is, u equals a sine, which consequently is du equals a cosine theta d theta. If you have this form, use the substitution u equals a tangent theta, which means du will be what's that? A secant squared theta d theta. And last but not least is going to be a secant theta, which is du equals a secant tangent in this case. Okay, what do you think about memorizing all this information? There's ways anyway, I'm not gonna lie, there's ways to memorize it, but do you feel like memorizing all this?
No.
The way I went about trigonometric substitution, I didn't ask you to memorize anything new. All I encourage in this case is just to keep in mind what you already know, which is the trigonometric identities, and just have a deeper, and the only thing we did is just have a deeper understanding of what Pythagorean theorem is, depending on the different forms, you know, like difference of squares. Let's see, that's hypotenuse minus side, sum of squares, side and side. That's all we need to understand. That's it. Now let me do one example using the long way. Well, so what was the okay, so that's the integral. I said I was going to go back to letter C. The integral of 1 over the square root of 9x squared plus 4 with respect x. Okay, so number 1, well, on the exam, for example, you're not going to have this table. You're not going to have a cheat sheet to rely on comparing the integral with the forms. So again, you will have to memorize them. You mess up a sign, you mess up a derivative, the whole problem is going to be wrong. So that's the issue with having to memorize all these 3 cases. Actually, the 2 semesters I taught this class here, I used a similar approach. However, I decided to move into this direction to avoid you guys into having to memorize a lot of info. Well, number 1, oh yes, this looks like a sum of squares. That has to be the substitution u equals a tangent. All right. And in this case, well, let's rewrite the integral to identify the u and the a. So that's the square root of 3x squared plus 2 squared. And, well, this means this is the u, and a, which is 2. That means we're going to use the substitution u equals a tangent theta, where u equals to 3x and a equals to 2. I mean, some of these elements that I'm going to write are going to be similar to the other approach. Now, here is what the book does. Okay, substitute. Oh, actually solve for x. Solve for x. X equals to 2/3 tangent theta. Dx equals to 2/3 secant squared. Well, this is the same as the previous approach. Right? This has to be the same when it comes to getting the dx. So that's fine. Now, so that's going to be the integral of the square root of 3x quantity squared. That is, the 3x quantity is 2 tangent theta squared plus 4. And the du is going to be 2/3 secant squared d theta. All right, let me continue over here. So this 2 squared is going to be the square root of 4 tangent theta plus 4 and 2/3 sine. Oh, let me do it over here. Yes, square the tangent. And well, to simplify, the textbook approach and pretty much every single calculus books, which is this approach, is to simplify this radical using a number of steps. So number one, notice that we have a common factor of 4. Agree? Yes. Factor out. And well, what's the square root of 4? 2 tangent square theta plus 1 and well, we can further simplify this radical because we know that tangent squared plus 1 equals secant squared. And again, these are not identities that we usually memorize, right? The one that we usually memorize is the sine squared plus cosine squared. But again, you have tricks to derive them whenever you don't have any access to a formula sheet. But I mean, it's annoying to just go back and forth between all this. Now, I'm not going to simplify anything just yet. So that's a 2/3 secant squared theta d theta. And that's 2 times the square root of secant squared. And this square root of secant squared can be simplified. Okay, let's compare all this. Now, with the triangle and with this quotient, we were able to go from this integral to that integral in one step by doing this quotient, the quotient of the radical over the number. All right. However, the textbook way, it's asking you to do 1, 2, 3, 4, 5, 6 steps before you get to the integral. So the moral here is radical over number saves you how many steps? 1, 2, 3, 4, 5, 6 steps. I mean, it's doable. It's not the hardest thing in the world, but do you want to do that for every single problem in the homework, in the worksheets, on the quiz, on the exam? So, of course, if you prefer to do it this way, do you feel more comfortable doing it this way, that's fine. It's still acceptable, but I mean, recall that on an exam, on a quiz, time is crucial. Okay, so of course, I mean, you have this video, you will have these videos on Canvas, so you can go back, so you can see the differences, so you can compare between one way and the other, so you can see the advantages and the disadvantages of going one way or the other.